So when you say stability, you're talking about mode stability, I guess? Like you look for a linear like solution and you look at
yeah, so stability to non-radial perturbations. They don't have to grow exponentially because the base state is itself evolving, but it's whether they grow faster than the base state. Yeah, yeah, yeah.
When you say asymptotic, when you say at some point you do asymptotic analysis, do you mean asymptotic in what? Like in n going to 1 or like the region of mechanical field? What do you refer to?
So yeah, in that talk, the prime limit was the rim is much thinner than the tissue as a whole, which is reflected in the death rate being much smaller than the growth rate. So I didn't say that, but you can formally extract a small parameter.
Oh, okay.
Yeah.
So the small parameter is the thinness or is
the place it comes from is my capital K being much smaller than little k. The implication of that is that the rim's much thinner than the, yeah.
Well, let's begin with our second lecture on multi-phase modeling of tissue growth.
Thank you. Yeah, so as implied, I'm going to do multi-phase, so I better say a few partly repeated comments on why. So the first thing I'm going to do is make cells out of water. So I'm going to have two phases, right? So in the first talk, cells magically made new ones from nowhere. Water is the main constituent. So the next level up is those two phases. More generally, if you're doing growth of tissue made of multiple cell types, there are all the different cell types. There's the extracellular matrix and the water and anything else you need for growth. So in principle, you can worry about a large number of cells. In the biofilm context, you can have multiple kinds of bugs in the biofilm, and biofilm have their own matrix, EPS, and again, water. So subcellularly, you can worry about it as well. There are multi-phase models of cell motility to relate to what else is going on here. So you'd have the phases would be actin and cytosol and so on. I'm going to do two approaches. The first I sort of view as conventional. It's how we used to do it. It's how a number of other groups have done it in the biological context. It's not now my preferred way of doing things, but it's the most transparent to describe physically. So that's where I'm going to start, and I am going to relate the two approaches. So N is I should start with the continuity equation. Sorry, it makes it clearer. So N is cell volume fraction, as earlier. I'm now no longer in 1.5 territory, so I'm going to need different velocity fields for the two cases. I'm going to keep the growth rate more general, but I'm not going to worry about nutrient in this talk. So that's one of the two continuity equations, the conservation of mass equations. I am making cells out of water, so the water phase has the negative sign, but with the same rate of transfer between phases. And as before, the phases are individually incompressible, so their volume fractions add up to 1. I've written that in multiple dimensions. Almost nothing will be multidimensional, and for two reasons. One is that I'm going to end up with a ridiculous number of surfaces if I do that. Writing down the models in higher dimensions is an immediate generalization, but a lot of the consequences are not, and I can already demonstrate one of those with these. So in 1D, if I add the two together, those terms cancel because of that. I combine those terms and those terms cancel, and then you integrate, and at least in the symmetric case, you've got an explicit relation between the two velocity fields, which immediately tells you something different from before. The velocity fields have to be in the opposite directions. You have to have water going in for the cells to grow out because the water is making the new cells. Whereas in the 1.5 phase thing, they both go in the same direction. Right, so that's the mass setup. Now I need the momentum equations to close the model. And now I will go straight to 1D. So in the cell phase, there's a cell pressure, how the pressure the cells exert on each other. You want to weight that with the volume fraction of cells, so you get that term. I'm going to do Stokes as before. So there's going to be a shear viscosity, Vnx, x is the viscous effect within the cell phase. And then there's the interaction between the two phases. So there's an interfacial pressure, which is P subscript capital I times Nx. So when there's a gradient of N and you've got some interfacial pressure, there's a net force in the x direction. You think about the thing narrowing, there's a net force that way. And then finally, there's the Darcy drag between the two phases. And again, it's low Reynolds number, so we've got zeros on the right-hand side. So that's the cells. The water phase is exactly analogous, except you might as well take it to be inviscid, so I won't write down that term. This is pi times by symmetry Wx minus kappa, and then opposite sign in the Darcy term. Okay, so that's not quite a closed system because I've now introduced three pressure fields, the interfacial pressure and the two pressures within individual phases. But I need to label these first. So those are the effect a phase has on itself. So they're the intraphase interactions. And these are the interphase, what effect one phase has on the other. Okay, so how am I going to close the model? Well, I need two more equations. I'm actually going to introduce a third, which is a overall pressure P. And I'm going to specify the pressure within the cell phase to be this pressure, which could just be the water pressure, but I want to keep symmetry between the two phases. And then you specify some interaction term between cells as capital sigma of n. Do the same by symmetry to the water phase, although, as I say, typically one would take sigma w to be 0. N plus w is 1, so there's no loss of generality by writing things just as functions of n. And then finally, the interfacial pressure, similarly, P plus sigma I of n. And then if you specify those sigmas, you have got a closed system. You've got the same number of PDEs as variables. Okay. So now I will reinstate the intraphase viscosity later, but for the time being, I'm going to cross it out. And now the next step will be something that only works in 1D because there's an exact integral because the overall momentum has to be conserved. That's true in any dimensions, but in any dimensions, that's a divergence, not a derivative. So if I add these two together, a lot of stuff cancels. In particular, these things cancel, and those obviously do. So we end up with, and again, with zero pressure boundary conditions in 1D, we can write the combination of pressures to be of that type. Okay, so I've done two first integrals, one from the mass equations and one from the momentum equations. And now I will copy from notes rather than trying to do it on the fly. I can eliminate essentially everything in terms of specified functions of n. Okay, so I know everything here in terms of p and these specified functions. They have to add up to 0. So we end up with p is minus n sigma n minus w sigma w. Pn is w sigma n minus sigma w. And by symmetry, pw is n, and then the opposite signs. Okay. So that comes from the overall momentum, overall conservation of momentum by adding the two momentum equations at the top together and integrating once. Once you've done that, you can use either of the momentum equations to determine the difference between the two velocities associated with the Darcy drag between them. For reference, I haven't written down sigma Ei. So the interfacial pressure, the pressure each phase exerts on the other one, ends up being that there. Okay, so if I use either of the momentum equations to determine the velocity difference, you get Vn minus Vw is equal to minus Kn times Nx. I'm not going to tell you what capital K is because it's a horrible mess of those various sigmas, and it's not going to be important for anything I say. But the point is the equations on the top of that bottom board are all specified functions of n. So you stick them into the derivatives at the top, and everything just involves the n by dx multiplied by some nonlinearity. Okay, that's one relation between the velocity fields. The other comes from conservation of mass, which I wrote on the previous board. So both the velocity fields can individually be written in terms of the gradient of n. And in particular, and again, d is a simple function of capital K, which I'm not going to tell you what that is either, but you can reduce those to Vn being of the form gradient of n multiplied by some nonlinearity, which you in effect specify as a function of n. Okay, so we're now nearly done in this first version of the model. I'm not going to take you much further. The only thing that remains is to stick the relationship over there back into the first of these equations here to give a reaction diffusion equation, which is what tomorrow's talk is going to be about. Okay, so finally, and the final version of the model is a reaction diffusion equation. I criticized Fisher earlier this morning. This is similar structure, but it's come from a completely different place. Okay, so general quasi-linear reaction diffusion equation. Crucially in 1D, right, the conclusions go over to radial symmetry. They don't go over more generally, and I will comment on that later. The other thing I wanted to say about that at this point is these are nonlinearities are very arbitrary. S is the growth rate, so you probably know a reasonable amount about that. This capital D involves all these things I described as specified over on the right. So it is worth worrying about very general forms of this equation. And that's sort of what tomorrow's talk is going to be about. So that's the first thing, first version of multiphase. So I think thinking in terms of interfacial pressures and intraphase pressures is a helpful way to think about it, but there's at least two problems with it. And that's what drove me to do the second set of stuff. But so firstly, how generalized to hide more phases? Right, that is sort of clear because this only works because you can write a single interfacial pressure, which when you add the two together, because you've got to conserve overall momentum, automatically cancels because n plus w is 1. It's completely unclear how to do that when you've got more phases. So the setup I'll go through next does address that. There's a more subtle thing, but more immediate. So what about the energy equation? Which I will do for this model, even though it ends up making not much sense. So the second version, you do get a sensible equation that governs how some energy evolves. So how do you get the energy equation? Well, I'm going to reinstate this term now because I think it's helpful to see what's going on. You get the energy equation by multiplying this equation by Vn and this one by Vw. And the simplest way to get intuition into that is if you keep the inertial terms, then on the right-hand side, you'll have rates of change of kinetic energy if you do that. That's sort of why that combination is the thing you should be doing. So, I think I do want to write them all out again. Yes, I do. Okay, so I will do that in some detail because it makes an important point I want to follow through. So if I rewrite the original system in terms of some of the intermediate things I've introduced, I reinstate the intraphase viscosity term. There's a minus n sigma n x from those capital sigmas are typically called excess pressures. And then so that one I'm going to multiply by Vn. And then the second one, I'm going to multiply by Vw, and then I'm going to add them together. Okay, treat it as inviscid, and then just use symmetry between the two phases. So that's the combination I'm going to want to take. Right, so various of those various combinations then appear very naturally straight away. So we're going to get naught is minus NVN plus W, right? So energy better in some sense. Well, energy is not conserved, but you know the mechanisms by which you're losing energy. So this equation better embed them. So the pressure terms give you that combination because I've already said, well, I said here it was 0. It's d by dx of that is 0. There I imposed conditions that it was 0, but in any case, that thing differentiates out to be 0. So the pressure terms combine in that desirable way. If I take Vn inside the intraphase viscosity term, I get that, and then minus the dissipation term. So you're starting to see things you expect to see. Okay, so that term has a sign, it's necessarily negative. So that's the loss of energy due to friction within the phase. And then if you look at what's happening with the final terms, the kappa terms, they've got opposite signs. So you end up with the viscous dissipation terms between the phases. Okay. So you've got some effects that are conservative. You've got the correct dissipation terms, but then you've got a pile of junk that has no physical interpretation. And that's another problem with this setup, and is why I think it's not the way to go. So for probably vacuous to write it down, but I will do for the record. You get all this extra stuff which doesn't have any natural physical interpretation, and you can't manipulate it in any sensible way to get one, as far as I can see. Okay. So that is the energy equation for the model in this form. And I disapprove in the sense I don't know what these bits mean. So they don't seem to embody the right physical concepts. So that's version 1, unless there are questions on it. Okay, so version 2 is a sort of semi-variational thing. How did I head this? Right, so version 2. And this is based on Rayleighan's. So Rayleighan dissipation functions, which I'll explain shortly. I think it gets various other names. I think Gonzaga gets his name associated with a similar approach. And lots of people do this kind of stuff in slightly different guises. So the point is we have got dissipation here, so we can't just use standard variational setups. So we're going to have to add something extra. So I do still want to have a free energy, something that doesn't dissipate. And that's going to be a statement of how the phases interact with each other. So I'll call it curly F. I'll write it as an integral over the usual domain, the tissue domain, of standard F, which is a function. I'll write it as a vector. I'm sorry, if you're not used to vectors being underlined, I'm sorry. That's how we tend to do it. So n is the vector of unknowns. The components of n, the different phase volume fractions, are going to be ni. And that's integrated with respect to x. So that's the free energy. Tells you quite a lot about how different cells interact. So the recipe to derive a set of PDEs from this Rayleighan approach is to take your free energy and first differentiate it with respect to time. But in order to do that, I need to specify how the various phases evolve with time. And they're going to go in the usual way. So this is stuff we've seen already, except I'm now using I, and you probably can't see that. I'll put it up in a minute. I is the label for the individual phases, and the transfer between phases is SI. Okay, so that holds for every possible value of I for the various different phases. We've got overall no voids. The volume fractions have to add up to 1, and the transfer between phases, unlike earlier today, is going to add up to 0, because I'm going to want to be making everything out of something else all the time, rather than gaining on missing maths. So I don't know how much needs repeating in terms of what's visible. So those are my mass conservation equations. They're not prescribed as anything to do, they're prescribed beforehand, not part of the variational structure, which I'll come to more in a minute. So that's part of the setup. I'm going to end up having to introduce a dissipation function as well to get to the end of the line. So the next thing you do is differentiate Right, Raelians I think are quite magic, and I'm going to explain why they're magical, at least some of the reasons I think they are as I go through. But there is a profound question as to the extent to which they embody physical reality. In other words, whether you have to do things this way. So what is df by dt? Well, it's the integral of gamma and then df by dt inside. Almost whenever I appears, it's going to be a sum over all I, and I have to be slightly careful because you can't use Einstein's summation because the number of times I appears in various places varies. Okay, so it's df by dni, dni by dt. Okay, so at this point I'm taking f to be only depending on n itself. There's other circumstances, and I may get to one at the end where you want it to depend on derivatives and things as well, but I'll come back to that. But I do want to track natural boundary conditions as well. So when you do the time derivative of the integral over the evolving domain, there's an extra contribution from the fact the domain is either expanding or contracting. So there's that contribution on the interface. Okay, so now I'm going to replace dn by dt from the continuity equations and then use the divergence theorem. So that's going to be sum over I integral of omega ni vi dot grad mu I chemical potential dx. So mu I is defined to be df by dni. So I've used the divergence theorem, so I'm going to get some extra contributions to the interfacial terms. So Q nu F, I'll write down what I remember and then see if it's right in a second. N mu I vi dotted with the unit normal. So that's directly from divergence theorem. And I've missed one set of terms. So dni by dt, I missed them because they tend not to matter. There's the integral over the domain of Si times mu I dx. So they will play a role in the energy equation, as we'll see later. Okay, so that's routine manipulations using the conservation of mass equations to get to a different version for df by dt. Then the core part of the method of Raelians is to combine df by dt with a dissipation function, which is the non-variational part, which captures the fact that you're not conserving energy. So then, and this again is pursuing the recipe, introduce capital R Raelian, which is df by dt, the thing I've just calculated, plus the dissipation terms, sum over I integral a half. So the intra-phase dissipation, as we've seen in other contexts, is going to be VIX. Again, I'm going to check this in a second. So that's supposed to be the intra-phase dissipation. So it has a sign, it's an exact square, as is the interphase one. So a half, and I need to have a sum over I and j, because this is the interaction between two phases, kappa ij, vi minus vj, all squared, is the dissipation between the phases. And there's one term forgotten because you need to enforce overall incompressibility. So I introduce pressure as a Lagrange multiplier, and then Ni, Vi, X, sum over all those. Okay, so you sum all the you sum all these equations using those equalities, and you get the d by dx of the sum of the Vi Ni is 0. And so overall incompressibility you enforce usual way with a Lagrange multiplier, which ends up being the pressure. So that needs to be a quarter. So the interphase dissipation double counts because there's kappa ij and capital Ji, which without this generality are the same, but you need a quarter to get the count right. Okay, so that's almost the final step. That defines the Raelian. The final step is to take the variational derivatives of the Rayleigh, specifically with respect to the velocity fields. Right, so these things are in effect variational derivatives already, so they've appeared in one context when I've been evaluating df by dt, but that's variational derivatives with respect to the ends. At this point, I do it with respect to p and vi. So the next step is to do dr by dp, variational derivative is 0, and dr by dvi is 0. And that will give me, so the Euler-Lagrange equation is based on that. So a partly variational argument. This is now a variational step, but it's in effect assuming the NIs are known, whereas you then have to go back and prescribe them from the mass conservation equations. But we'll see almost straight away that it's not giving you nonsense. So I'm about to write down my governing PDEs, which do resolve both of the problems I'm now rubbing out, because I haven't specified the number of phases here. And we'll see how the energetics work because of the underlying variational structure. Okay, so the variational derivative naught is, if I start with the final term, so dr by dp is something I've already alluded to. It's the overall conservation of mass. I won't write that down again. dr by dvi, I'll start with the pressure term. So that's nivi dp by dx. Okay, so it's got the opposite sign from how you normally write it down, because everything will have the opposite sign, and that vi shouldn't have been there. I'm taking the variational derivative with respect to vi. So that's what the final term gives you, right? You're integrating by parts to extract the vi out the front. But that will give you a contribution to the boundary, the natural boundary conditions, which we'll see. So what else we got? We got df by dt. So the place the vi's appear in df by dt is here. So taking the derivative of that with respect to vi, there's an ni mu ix. So there's in effect an extra contribution to the pressure, which is different between different phases, and is the chemical, in the thermodynamic jargon, the chemical potential for that phase. Right, so what I wrote there can't have been quite right. No, it wasn't. Sorry, it's not an important thing, but you're weighting the dissipation with Ni. It doesn't appear inside the dissipation. So that's the viscous dissipation within the phase, and it has to be weighted by the amount there is of that phase. So that term then gives you, write it in the same order, NI, VIX, X. So the usual term you get in Stokes flow, the viscous contribution, and it's 1D, so there's only one viscosity. And then the final term comes from the interphase contributions. So Kij, Vi minus Vj. So those are my governing PDEs. You may wonder why I'm doing all this, right? Well, the punchlines, I think, will be then the list of comments I make about what structure these equations have. And that's going to follow shortly. There's one final thing I need to say, which is how the boundary conditions come out of this. So we've already got these contributions to the boundary. To derive the Euler-Lagrange things, you do the usual thing of perturbing Vi by an amount I'll call capital Vi. And correspondingly, you have to perturb the evolution of the domain Q nu by capital Q nu. So I'm going to write down some extra boundary contributions from that, and then talk about the boundary resulting boundary conditions afterwards. So say I've perturbed little vi by capital Vi, and then doing the integration by parts on the p term to get this first term in the momentum equations will give that contribution on the boundary. And the other contribution on the boundary comes from the additional contribution comes from the viscous term there. So that will be VIX. And then if we get this right, VI. Okay. So integrating by parts on that term will give you that as the contribution. So you've got to do the same here. So I can write down the general form of how the boundary conditions get perturbed under this kind of argument. So the overall boundary contributions are there's Q nu, the perturbation to little q from that term. There's the perturbation to EI from that term. We're now in 1D, so things look a bit simpler. So there's that stuff. And then, sorry, I lost another bit as well. No, I didn't, it's there. Yes, I've got that, sorry, apologies. And then these new bits here. So there's minus P times Ni Vi. Finally, there's Ui Ni dVi by dx times Vi. And this is all the sum over all the values of I. Okay, so having gone through all that pain, I hope I can make some use out of it. So the first thing I want to check is overall conservation of momentum. Okay, so there's various sanity checks I want to do on this and then some interpretation. So overall conservation of momentum involves adding these equations all together. So in particular, those ones are going to cancel between phases because the I and J terms have opposite signs. This one is going to stay in divergence form, so that's going to be conserved. This one will work because the sum of NI's is 1. The awkward one is there, so we've got to check that one conserves overall momentum. So sum over I of the momentum equations. And I will swap the signs over to write it in more conventional form now. There's naught is minus Px. Okay, there's the usual pressure gradient term you see in Stokes flow. And again, that's because the NI's add up to 1. There's minus, the rest is sum over I, so let me write it all down at once. Ni, and I need to reinstate what mu I was to make the next step clearer. That's dFi derivative, and then there's the sum over I of the various interphase terms. So since they're inside the sum, I only need a minus sign. Ni. I sometimes regret putting talks with lots of suffixes in. Sorry. Right, so that's the overall conservation of momentum equation, which better be conservative. So 2 of the terms in it are immediately so, they're exact derivatives. But it's then clear that the rest of it is as well. So that's Ni dF by dNi minus F by the product rule. Okay, so if you differentiate down what I've just said, you're seeing there's a Legendre transform in there, and that gives the F terms on the previous line. And then there's the remainder, and I've failed to write the sum, but I hope it's implicit. Okay. So first sanity check is that the overall momentum is conserved. And that's to do with the place it's come from. That's to do with the variational structure. So what do I want to say about boundary conditions? I want to check that that's giving me something sensible as well. So here, I think the cleanest way to see what's going on there is let, in order to deal with the boundary, I'm going to subtract off the normal velocity, which is in 1D is just the velocity, right? Right, Wi. And similarly, the perturbation I use to derive the Euler-Lagrange equations. Vi is going to be written in terms of Wi then. And that tells you what sensible boundary conditions are. And then I can leave all this messy calculation and say something I think is more instructive about the structure of this model. Okay, so the remaining terms involving Q nu from this mess here are the ones I've just written down. And then the remaining part is the difference between the velocity of the boundary and what would follow from the kinematic condition, which will tell you there's two different kinds of boundary condition which naturally arises. And I don't there mean natural in the usual sense in variational problems. Okay, so typically you'd either take one or other of these brackets to be zero, and both of them have natural interpretation. So the final thing I'll say about model setup is in terms of that'll give me the boundary conditions I would want to be specifying in order to close the system. So you might think of the phases in two different ways. So on the boundary, some of the phases may be glued together. So maybe different cell types. There's another phase, there's some phases that wouldn't be. And the typical one there is water, because water can get in or out of the tissue. So the natural choices are so one, if I specify that the WIs all have to be zero, so that those phases are moving with the free boundary velocity, the boundary conditions you impose on that phase are Vi is Q nu. So those phases all satisfy the kinematic condition, and that defines the edge of the growing tissue. And the other natural choice is, instead of specifying the W's to be zero, we specify the terms they multiply to be zero, which I guess is closer to the conventional meaning of a natural boundary condition. And that means for those phases individually, they've got zero stress boundary conditions. So that's kinematic for some of the phases and zero stress for some of the rest of them. And then finally, there's an overall stress balance that has to be zero, which gives you the right number of boundary conditions. Okay, so I hope that's the most painful part of this talk done. You sort of have to go through all those steps to get to a sensible answer. But now I want to try and indicate why I think it's sensible. So a series of comments now. Any questions from the around? Okay. So notes. If you've been tracking it through, I haven't included surface energy. So the way surface tension appears in these Rayleigh setups is you add an extra contribution to the free energy, which is the area of the interface. And if you track through what that does using exactly the same arguments, you get surface tension boundary conditions. So including surface energy. In F leads to surface tension, which is consoling. That's something you'd hope to happen. Okay, so surface energy is essentially, in the simplest case, just a multiple of the surface area. So I've made a virtue of the fact that overall momentum is conserved. That better be true if you generalize the model. And there's two senses in which you might want to generalize the model. One, of course, is high dimensions, but the other is making F depend on the ends in a more complicated fashion. So more general F. higher dimensions. Leads to. Okay, so there's this statement up at the top with Ni df by dni d by dx better be conservative. More generally, that comes in the form of what do we want? Sum over I grad, Ni grad the variational derivative, in other words, the chemical potential. Right, so it may or may not be clear that that is that does sum to a divergence form. And you need to know a bit about Noether to see that. So that's sum over I div of grad of Ni df by dni, and then minus dni by dx. So the first, df by dni grad ni. Right, so the first bit in that sum is definitely in divergence form, so that's conservative. So why is the second bit? Well, you know the second bit is as long as you specify f to be translation invariant in each of the spatial variables. So if you do that, that's exactly the thing that comes up in Noether's theorem associated with that variational symmetry. So any sensible generalization of the original free energy, and indeed going to higher dimensions, gives you something that makes sense in terms of conserving momentum, which better happen, which is conservative, which is a divergence form. By Noether's first theorem. So that's a statement that the variational structure of f matters, that we've used variational derivatives in going from f to df by dt, and the implications of that arise there. But there's also underpinning that, there's also variational structure to the R problem, the Rayleigh problem associated with the dependence on the V's. So correspondingly, R is invariant under constant shifts of the velocity under VI, as you can check, to VI plus U for constant U. And that's only true because of the previous statement. Okay, because the chemical potentials are related in a particular way. When you translate V by a constant in this variational statement, all the extra terms are of divergence form. So that's a variational symmetry as well. So in the classical mathematical physics kind of way, invariance under spatial translations gives conservation of momentum. And conservation of angular momentum follows similarly. Okay, so F in particular, F is invariant under the usual assumptions under rotations of coordinates. So the most obvious physical principles from continuum mechanics do hold up in this multi-phase setting. Okay, so one of the ways I wanted to lead into this was how the energy equation doesn't make any sense in the more conventional way of dealing with these multi-phase problems. So that'll be the next statement. And that'll be Noether again, but in a different guise. Right, so energy equation. So same game, you multiply each momentum equation by the corresponding velocity. And we get 0 is sum over I, and then a right mess. But then we see how things simplify. So the VI I've just written down comes from the fact I'm multiplying each equation by the corresponding velocity. And if I group two of the terms in the way I'd written the momentum equations, you get that combined pressure effect, which includes the chemical potential in each case. Then you get the intra-phase viscous dissipation, which we saw in the earlier guys does work. It does end up giving you a sign, so positive dissipation. And that'll be true here. It's again these bits that where the complication comes in. And plus sum over J, Kij, Vj, sorry, Vi minus Vj. Okay, so that's a routine manipulation. I've taken my original momentum equations, multiplied them by the corresponding velocity fields, and just written the thing down again. And now the playing around with it comes in. Okay. So that equals sum over I. What happens now? Minus Vi Ni P plus mu I times X. Okay, that's taking the Vi inside Vi times Ni inside the derivative. That's fine with the P term because the sum of the Vi Ni differentiated with respect to X by overall conservation of mass is 0. So that's the only contribution you get from P, but there's something missing here. So by the product rule, I have to add this thing back on to keep track of all the various contributions. And that's going to end up being the most significant term. And that's where the bits of magic come in again by Noether. And then the remaining stuff is fine because this thing, you can take the VI inside. So that's the flux of energy associated with the intra-phase viscosity. And then the rest of it has a sign, so minus VI Ni VIX all squared. So that's the viscous dissipation within each individual phase. It's got a minus sign in front of it, so all's well. And then this, if you remember, kappa is without loss of generality symmetric. So you can combine those terms, the half to deal with the double counting again, and you get a sign. Okay, so we're nearly done on the energy equation. It's the second term in that second sum that's in the first instance the troublesome one for the same reason it happened in the first version of multiphase I did. This combination you may recognize as appearing in R. So R involves half of the dissipation. That's the dissipation that appears in the energy equation. And the half is to do with the fact that you've got the quadratic nonlinearities there. Okay, so what happens with that extra term, which doesn't appear to be saying anything sensible about energy, at least in the previous guys. So now I'm going to focus entirely on that term because it's not in divergence form and it doesn't have a sign. So this is the thing I have to worry about. And as I say, where the magic comes in. But the first thing you notice is VI NIX is exactly the thing that appears in the continuity equation in the conservation of mass. So that's equal to minus sum over I, recalling what the chemical potentials are and keeping the thing more general now in order to see why Noether matters. And we've got the time derivative. So if F just depends on the Ni themselves, that's immediately an exact time derivative. But more generally, invariance under time translations, as usual in mathematical physics, will give conservation of energy. So that's one part of it. There's also the SIs there. So plus sum over I, mu I SI. Okay, so that is minus df by dt minus the spatial divergence again by Noether's first, and I'll write that down in a second, plus this extra term, which isn't conserving energy. And I'll also comment on that in a minute. So what's going on here? You take the dF by dt over to the left-hand side. So you've got a rate of change of internal energy, if you like. Can't spell spatial. You've got various divergence terms which tell you the flux of energy, but conserve it. They are divergences. You'll notice, incidentally, I'm swapping between dimensions as well as I go along, because the same conclusions go through in high dimensions. And then you've got the dissipation terms in the usual way, that you lose energy from friction. But then we finally got this term. So that's the one I need to comment on now. Incidentally, I notice I've changed my numbering system from little i's to 1, 2, 3's, never mind. So the two things which imply that, so by invariance of F under T translations. Okay, so there's no explicit appearance of T in little f. It only appears because the NI's depend on T. So the standard thing with variational symmetries, that curly f is invariant under translations of T. So again, that's Noether's first theorem. Variational symmetry leads to a conservation law. And the second part, and this term here, is the energy change by changing phase. Okay, so I think you sort of think of that as being biological rather than physical. Normally, you wouldn't want a term like that in physics. The argument here is these kind of models don't include cell metabolism. So cells can burn energy to divide or differentiate or whatever. And that's embodied in that term, that there's a shift in energy when cells swap phase. Okay, there's a few more points to come. Any questions on those ones? Right, so those are things that convince me that the Rayleigh setup is a good way to formulate these problems for multiple phases. The obvious sanity checks will work in a way they don't work for the more conventional approach. And I should say lots of people are doing similar things to this. I don't know if they've gone the same route all the time. Okay, so the next comment I'm going to make goes back to 1D and is to do with the reduction to reaction diffusion equation that I obtained from the first multiphase formulation. It goes in exactly the same way, so I only need to make a single statement, which itself has physical interpretation. So with nu I equals 0, so I throw away the intra-phase viscosity. I only have the Darcy drag between phases, which isn't a draft thing to do, to be clear. Total momentum conservation. In the case I've largely concentrated on, where F just depends on Ni, gives. You have simply a grad. Well, in fact, let me write that down. So grad of P plus Ni nu I F sum over I is equal to 0. Okay, so in higher dimensions, that's problematic, and I'll comment on that in a second, because you've gone from having the same number of equations as dimensionality, the grad, to having a single equation, because that thing can only work if P is given in terms of F in a way I'll write down in a minute. But in one dimension, it's fine and tells you what P is and gets you to the reaction diffusion equation I wrote down earlier. So up to a constant shift in pressure, which doesn't matter, that gives you that relation between the pressure and the free energy. So what is that? That's familiar in thermodynamics. So that's a Legendre transform between different, you can think of it as different thermodynamic potentials. And the physical interpretation is a balance between the physical pressure, the hydrodynamic pressure, and what in other contexts, so I don't think it's useful terminology here, would be the osmotic pressure. So balance between hydrodynamic and osmotic pressure. Okay, so there's some good news and some bad news. The good news is in 1D or with radial symmetry, you get an explicit expression for P in terms of the concentrations, which allows this reduction to a reaction diffusion equation. In higher dimensions, it doesn't make sense, and you have to reinstate the viscous terms. So I will now say that and then move on to another point. So why does it fail in higher dimensions? There's a clear mathematical reason, which is Noether's second theorem, which is the thing I'm about to say. That doesn't help you physically, but at least in effect gives you full warning that there's going to be a problem. Right, so Noether's first theorem says if there's a variational symmetry depending on an arbitrary value of a parameter, it gives you a conservation law. The second theorem says that if the variational symmetry involves arbitrary functions, in this case of the space coordinates, then there's a degeneracy in the Euler-Lagrange equations. Sorry, you can't read the bottom of that, with apologies. So it says there's a balance between hydrodynamic and osmotic pressure. So the problem with what I wrote down there, this leaves the problem underspecified in high dimensions. So for D bigger than 1, and that's Noether's second. The Euler-Lagrange equations don't suffice. You need some gauge condition. Noether's second. U, I had the translation of U of the velocity, each of the velocity fields by the same U. Just satisfies, instead of needing to be a constant, it's any incompressible velocity field. So it contains D minus 1 arbitrary degrees of freedom. Okay, so the message of that is if you're going to do the high dimensional case, you can't simply throw away the intra-phase viscosities. Right, then the final set of comments, and if I've got time, I'll do one, see how much I can say about one specific application of this kind of setup. The final set of comments relate the two different approaches to setting up multi-phase models, which say the second is the one I much prefer now, but the first does have the virtue of, I think, rather more direct physical interpretation in terms of what the different pressures are doing. So I finished this list with that. So comparison with the first approach, the one involving the capital sigmas in the two-phase case. Okay, the first deduction to make that comparison follows from the overall conservation of momentum. So in the first way I did it, you add the two momentum equations together. In the first guise, that was the combination of pressures that appeared. In the second one, it's the thing involving the Legendre transform. So it's n mu n plus w mu w minus f. Okay, so that's, you're wanting to think of that as what an equation relating the PNs and the PWs. It's only one equation for two unknowns, but there's sort of only one natural way to decompose it. So the natural inference from that is P is evenly distributed between the two. N plus W adds up to 1. So we can distribute the P in that way. F appears in the same way, and I'm going to end up adding F to the pressure to cancel the F's out again. At this level, they're a needless complication. So that neither of those are specific to a phase, but then in a quite natural way, the individual chemical potentials are. So sort of the only natural way to decompose the previous equation into separate relations between the cell pressures and the water pressures are the way I've just written down. So now do P to P plus F to get rid of the F, which is going to distract me otherwise. And then recall Pn was P plus sigma n. So sigma n has a rather natural interpretation as the chemical potential, and similarly over here, sigma W is mu W. So none of that's very surprising. The slightly non-trivial consequence of it is what the expression you get for the interfacial pressures. Okay. And I won't go through the steps of the algebra. I'm getting tired, but the formula that allows you to extract it is the pressure terms from the N equation. So in the second version of the model, they take that form because I've added F onto the pressure. And then in the second version, the first version rather, that was NPNX plus PI NX. So straightforward piece of algebra you can do in equating those two sides, and the expression I've just written down for Pn in terms of P to get the expression for Pi. Okay. So that ends up giving you the 2 lines of algebra. What I'm going to do something that looks like a bit like a Legendre transform, but the variables are the wrong way round. So the interfacial pressure is related to the chemical potentials in that way. So I don't think I've ever seen that kind of relation in thermodynamics. So if anybody has, please tell me. It's not the standard kind of relation between thermodynamic potentials you get. So that's what happens in the 2-phase case. But an extra payoff is you can do the same calculation on the new version of the setup, the Rayleigh one. You can rewrite it in terms of the first version to get an expression for the interfacial terms, which I commented much earlier. It's far from clear how to do that in the first version of the model. So extending the thing I've just written down to more phases. Extending 5 to more phases. I'm minded just to write down the answer, largely because I'm running out of energy, for which I apologize. So what do we get? We get minus grad, same kind of terms as before. Okay, well, I had N times Pn and W times Pw before. So that's the form you get using statements I'm about to write down about the relations between the PIs. I better do that already. So PI is going to be P plus mu I, just as it was under point 5. So this cell, the intra-phase pressure within the cells is the overall pressure shifted by the chemical potential. And then the various contributions to the momentum equation are that one, just as I had in the first version of this setup. But then the interfacial terms are the important new thing you get from this reinterpretation. So you go through the algebra and you get a sum over J, because for phase I, there's no sum over I here, right? So the extra terms are the interactions of phase I with all the other phases J. It comes in 2 steps. think it's revealing to write both of them down. You get that term there, which looks very like what we had in the first setup. And that automatically sums to 0 because the NIs all sum up to 1, which tells you that that conserves overall momentum. And then the interaction between individual phases ends up being those terms there, which do have the required symmetry between the I and J phases in order that they cancel when you add up all the different phases to conserve momentum. So you think of the terms there, this is the effect of the I phase on the J phase and vice versa. And that actually simplifies down further if you use the statement up here in, I think, a quite appealing way. But I'm not sure you would have used a formulation anything like this in advance in multiple phases, because it isn't clear how to write down the interphase interactions. So you get a Newton's third law statement that the effect of one phase on the other is the same as vice versa, they cancel. So you can generalize my initial statement, my initial setup to this one here. But as I say, I don't think that's necessarily obvious in advance. Okay, I'll finish off by saying a few words about how cell sorting looks in this context. But any questions before I do that? Okay, so that was all a bit abstract, and I did want to finish with something a bit more concrete, though I'm not going to take it very far. In part is, I guess, to convince myself this way of doing things makes sense. It's flexible and does satisfy all the necessary physical constraints. But also, incidentally, points you at a model reduction. It's those physical constraints that lead in particular to the reduction to a reaction diffusion equation I've alluded to. Incidentally, tomorrow's talk is largely on slides, which probably means I won't exhaust myself quite so much. Right, so cell sorting. So there are lots of models of cell sorting of various types. I'm not going to take this to the end. I'm just going to say how it looks in this context, which is rather similar to the models in the literature, but has some slight differences. And it's going to be 1D only. So the models in the literature are high dimensional. But you can't, in this framework, you can't get to, incidentally, I'm going to end up with something like the Cartan-Hilliard equation. You can only get there in 1D if you start with this kind of setup for reasons that are implicit in things I've said earlier. Okay, so I'm going to have two cell types that make up some tissue. I'm not going to have them dividing, I'm just going to have them sorting. Right, so cell sorting is typically where you're trying to describe a collection of two different cell types or more aggregating into clumps of the individual cell types. So it's a pattern forming setup. So cell division is typically not important in that context. So the continuity equation is reduced to that form. As always, everything is one type or the other. Okay, so the consequence of that, as before, you add the two equations together and you get the counter flow of the two cell types in order to conserve the no voids condition everywhere. Okay, that's having the two continuity equations together. Right, I don't know how much more to say. Okay, so that they're the consequences of the conservation of mass equation. I'm going to save myself writing by just getting to the punchline of the conservation of momentum equations. So set, for the time being, although right at the end, I'm going to come back to two terms, what those terms do. So if you throw away the intraphase viscosities in the previous notation is of that form and go through what the conservation of momentum does, you can integrate the overall momentum as before and then use the Darcy relation to determine the velocities in terms of the, in this case, the differences in chemical potential. So combinations like that have appeared above, although not in an identical looking form. But that is the velocity field in a particular phase in terms of the phase volume fractions and the differences in chemical potential. So the driving force for the cell sorting is if you swap two cell types, you're shifting the chemical potential according to that difference at a particular point. Okay, so the equation you end up having for N1 is dN1 by dt is d by dx 1 over kappa. And now the symmetry between the two phase cell types comes in, as you know it must do. Okay. So once you've specified f and therefore mu1 and mu2 as functions of n, you've got a closed system because you can eliminate n2 in terms of n1. So I'm going to make two final comments about it. So a single diffusion equation, if you like. So you now have to decide what contributions you're going to have to put into the free energy, which in turn determines the mu for this thing to make sense. So this is the only time I'm going to generalize the free energy beyond dependence just on the ends. And I'll actually start with the more complicated one. So possible contributions to F. So penalize interfaces. Stop the thing becoming ill-posed when diffusion is backward, which I'll come to second. Slightly odd order in which to do it, but I think it's going to be simpler to explain. So if I want to penalize interfaces, I need functions that depend on the gradients. I imagine for many of you, this is very familiar territory. Might want one between the two phases like that, and then the second phase would be that. So because N1 and N2 are slaved together, it's irrelevant whether you keep all the terms or not. But the point is that that will give a contribution to mu1 minus mu2 of the desired type. So mu1 minus mu2 is proportional to minus n1xx when you take the variational derivative. So you insert that into the diffusion equation I wrote earlier, and you'll see you've got a fourth derivative term involving n1 xxxx, the thing in Cairn-Hilliard, which makes the thing well posed if the diffusion term is backward, which I'll come to in a minute. So that's to stop the thing being ill-posed, but I want to say it's not actually, in this context, it's probably not the best choice. And that does lead on to the clear PDE question, which, assuming I remember, I'll finish off with. Cell energies. So these ones have more natural interpretations, which is why I'm slightly skeptical about this one. So e.g., you can have the entropic type stuff, which would be something like n1 log n1 minus n1 plus n2 log n2 minus n2. Again, since my brain is starting to fail, I'm just going to write down the upshot. So that gives you mu1 minus mu2, all x, the thing that appears in the equation, as 1 over n1, n2, the n1 by dx. Okay, so if you choose kappa correctly, you can get a linear diffusion term from that, which is what you expect from entropy. The more interesting one is cell binding, so whether cells like to bind to each other or not. So there's minus signs because the energy decreases when cells bind. So n1 squared minus b, n1, n2 minus A2 over 2 N2 squared. So that's the one that gives you the backward diffusion term, just you do in much more familiar territory. So for the record, that's A2 minus B minus A1 plus A2 minus 2B N1. The term to focus on is the very final one I've written down. So if cells like to bind it to each other better than binding to the other cell type, then the thing in this bracket is positive. You get a negative diffusion term, a backward diffusion term. But conversely, if they prefer to bind to each other, you get a positive diffusion term, which is exactly what you'd like on physical grounds. Okay, so it's easy to go through standard arguments to get the Cahn-Hilliard type equation, and then cell sorting follows from phase coarsening, and the cell types will typically go together, same type to same type. My view is that these kind of terms are rather artificial in this context. In particular, they account for the fact that cells are discrete objects. I'm going to finish by saying essentially what happens if you reinstate the velocity terms, viscous terms rather. So very final comment, reinstating mu1 and mu2. Right, you can't end up writing it in a very revealing fashion. So I'm just going to jump to what happens in the linearization if you do this. Eliminate all complications just to see the structure. Eliminate complications associated with the various nonlinearities. So especially linearize. Right, and the kind of equations you'll end up with are dn by dt, the conservation of mass equation. When I linearize n1 about a particular value, it takes that form, and then the overall momentum equations look something like naught is the osmotic pressure gradient. The pressure gradient is associated with n and with the mu's in the previous stuff. Then importantly, I'm reinstating the viscous terms and ignoring all the parameters, and that's the Darcy-Drag term. So if you ignore that second spatial derivative, you get just the backward heat equation, which makes no mathematical sense, of course. But if I don't, I keep that viscous term there and differentiate to eliminate. The final thing I'll write down, the final punchline, is the equation you get. The pattern-forming equation is not Cahn-Hilliard anymore. As the backward fusion term, it's pseudo-parabolic. Okay. So that's sort of how I think cell sorting should be done in a continuum context. Okay. So the regularizing term is a third derivative, mixed derivative, rather than a fourth derivative, spatial derivative. And it does have important consequences. That doesn't phase coarsen in the same way. So the cells won't exclusively lump to their own type. You'll get different patterning. Right, I'm quite tired. I'll finish there. Thanks, everyone.
Are there any questions? I do have one question. So you still have a moving boundary for omega, right? What's the is it just convenience that the intercellular and the external boundary are treated so differently? I mean, just that you couldn't possibly do it.
Right. So because most of this second talk was abstract, I brushed quite a lot under the what do you brush things under? Carpet. I brush things under the carpet. So if you were doing growth, for example, growth of a tumor into healthy tissue, it's not the situation I talked about in the first talk. You'd have the two different phases coexisting and an interface between them. So you'd sort of have two copies of this model, one either side of the interface. Does that get at your question?
That's it.
Yeah.
Exactly.
Yeah.
All right. Well, hey, that's will rejoin at 2:30 to continue. Thank you.
Thank you. Thank you.